So our next topic is diffraction grating and grating equation. A diffraction grating consists of a very large number of extremely narrow parallel slits separated by equal opaque spaces. There are two types of diffraction grating: reflection grating and transmission grating. A plain transmission grating is one made by ruling fine lines at equal distances on an optically plane glass plate with a diamond point. So in this figure, you can see uh, around 6,000 lines per centimeter that is drawn on a plain glass plate with a diamond point. Transmission grating used in laboratories usually contain 6,000 lines per centimeter. So the width of the slit is of the order of wavelength of light. So now it is explained how we can make a diffraction grating. A thin layer of gelatin solution is poured over the surface of a rolled grating and is allowed to harden. When stripped from the grating, the gelatin film retains an impression of the rolling of the original grating. So then the film is then mounted between two plain glass plates to get a transmission grating. A reflection grating is made by fixing a film against the silvered surface. This is actually that we have our laboratory for doing our experiment. It's actually a grating look like. So now we are going to derive the grating equation. Transmission grating is generally an arrangement of a large number of slits that we have seen in the previous slide. In diffraction theory, we consider a transmission grating as a set of large number of parallel slits. A few are shown in figure. So here we can see a number of slits and in grating usually there are large number of slits that we can draw, like we can extend figure. Okay, so here actually only 1 2 3 4 5 slits are there, but in actual case there are n number of slits. So here the width of the transparent portion is A and that of the opaque portion is B. AB is equal to A and BC is equal to B. And the sum A plus B is equal to D is called the grating element. That is this much distance, AB plus BC. AB plus BC. If capital N is the number of lines per unit length, then we can write capital N is equal to 1 by the grating element is 1 by D, that is equal to 1 by A plus B. What is capital N? N is the number of lines per unit length. A parallel beam of monochromatic light is allowed to incident normally on a grating surface. The light coming out from the slit superimposed together and a diffraction pattern is formed in the screen. These diffraction beams can be focused by converging lens. In practice, the telescope in the spectrometer receives the pattern. Actually, diffraction occurs for waves from single slit alone and interference for waves from various slits. Hence, here a combined effect of interference and diffraction can be observed on the screen. Here we can see the diffraction pattern. So there is a central maximum here. So it is called the zeroth order principal maxima. On either side of central maxima, we can see the first order principal maximas and second order principal maximas. That is, here A and A dash belongs to n is equal to 1 first order principal maxima, and B and B dash belongs to second order diffraction pattern, and for n is equal to 2 is called the second order principal maxima. So the central maxima is also called as n is equal to 0 zeroth order principal. Okay, so actually the first order principal maxima make an angle theta 1 with the central line, and second order principal maxima with an angle theta 2 with the central line. And here it is derived, it is, explained that actually diffraction occurs for waves from single slit alone, and interference for waves from various slit. Actually, this can be explained using the detailed derivation of single slit, double slit, and n slit uh, derivations. There we get some equations. Based on that equation, we can explain the details of the combined effect of interference and diffraction. But for our KTU syllabus, we don't need the details of those equations. We just need to study what is uh, there. Okay, so what is happening there? So this is so we are just explaining the phenomena, the diffraction pattern. We are not going into detail in the, we don't need for our syllabus. Derive the grating equation. So the incident lights are incident on the slits. So let the theta be the angle between the diffracted rays, diffracted beam, and incident beam. So theta is called the angle of diffraction. So here we get two parallel lines. Not only two parallel lines, there are several lines for every diffracted light. So we can get a number of these parallel lines. So if we consider these two parallel lines, path difference between these two parallel lines is Cn, because we can take this line from A and this line from N. So the path difference is Cn. So we need to find out the path difference. So how we can find the Cn? So Cn will be equal to d sin theta. Cn will be equal to d sin theta. So here we can say that if we know the path difference, and we can substitute the condition for construct errors, because we know the condition for constructive interference, we can write the expression for principal, that is the condition for brightness. So Cn is equal to d sin theta. So for example, for nth order principal max, the path difference must be multiple of lambda, integral multiple of lambda. So we can write d sin theta is equal to n lambda, where n is equal to 0, 1, 2, 3 is called the order of diffraction. Is equal to 0 corresponds to central maxima. So in terms of lines per unit length, because we know 1 by d is equal to capital N, so we can write sin theta is equal to n lambda by d, that is n, the grating equation. So actually for from this equation we can write an equation for lambda. Lambda is equal to sin theta by nn. Okay. So this is here we can see the diffraction pattern. So as we have already told, the central maximum is there, that is zeroth order principal maxima. On either side of central maxima, we can see the first order principal maxima and the second order principal. But in between the first order, no, in between two principal maxima, we can see small pattern. So there also maximas and minimas are there, but the intensity is very. They are called second order, secondary principal maxima and secondary secondary maximas and secondaries minima. So in between the principal maxima, you can see small intensity patterns. So these also contain minima and maxima. They are called secondary minima and secondary maxima. Okay, so in actual case, we can observe the principal maxima because the secondary maxima is having very low intensity. We can see the principal maximas grating. So we can measure the angle corresponding to the principal maxima, and we can, using the grating equation, can find various parameters. Okay, so this is actually what we can observe if we use a white light source. White light source is used in our spectrometer experiment in our laboratory. So there we can see the VIBGEO. So that means for first order principal maxima, for central maxima, the diffraction pattern will be white light itself. And for first order principal maxima, we can see the VIBGEO. We can see the different colors separately. And for second order maxima, we can see the colors separately, but with a intensity drop comparing to the first order principal maxima. So likewise, for the third order also we can observe, but the intensity gradually increases. Okay. So we are going to explain how many secondary minima and secondary max be there in a diffraction grating interference pattern. So for that we need another picture. Here it is very clear, so we can see the secondary minimas and secondary minima here. So grating spectrum consists of a central maxima, that is n is equal to 0. This is called the zeroth order principal maxima or central maxima, and the others on either side of the central maxima. For n is equal to 1, it is called the first order principal. N is equal to 2 is called the second order principal maxima. N is equal to 3 is called the third order maxima. Okay, so the from first order principal maximas is produced on the either side of central maxima symmetrically. You can observe that. It can be shown that there are n0 minus 1 secondary minima and n0 minus 2 secondary maxima between two successive principal maximas. So I have already told you, we can see a small intensity pattern in between two principal maxima. So these small intensity pattern are called secondary maximas and secondary minima. So for example, N0 represent, capital N0 represent the total number of lines on the grating. What was capital N? Number of lines per unit length. Number of lines per unit length into total length of the grating is N0. So total number of lines in the grating. So we get. So N0 and N are different. So N0 is represent the total number of lines on the grating, but capital N was number of lines per unit length. So please remember that. So if N0 is a total number of lines per total lines number of lines in the grating, it can be shown that N0 minus 1 secondary minima and N0 minus 1 secondary maxima between two successive principal maxima. But these are of negligible intensity. So we consider the principal maxima whose angular positions are given by the grating equation. So previously we have seen uh, first order principal maxima is at an angle theta 1 and second order principal maxima theta 2 with the okay. So if there are 30,000 lines on the grating, so N0 minus 1 means 29,999 secondary minima and 29,998 secondary maxima will be formed in between two successive principal maxima. That many number of principal maxima and minima will be formed between two successive principal. Okay, but these are of negligible intensity. So while doing our experiment in laboratory with the grating spectrometer, we are only measures the first order principal maxima, second order only, so that we can see. Okay.